starting with the particle physics. So particle physics, we have the elementary particles, the elementary particles like the quarks. So starting with the quarks, these are spin half fermions. So this is spin half fermions. Now it has the charge. So this is charge Q is equal to 2 by 3 times the electron charge, 2 by 3 times the electron charge, and also you will have the charge equal to minus 1 by 3 times the electron charge. These both charges are possible for the quark. Now one important thing that you need to remember is quark is not a free particle, so due to this reason that the total charge cannot be fractions. This is against the law of charge. That is, the basic unit of charge is E, Coulomb. So it cannot have E charge. That is, some fractions of E is not possible. Either it has to be quantization of charge. This is violating the law of quantization of charge. What does the quantization of charge says? Quantization of charge. What does that quantization of charge say? That is 1e, 2e, 3e, etc. It cannot be fractions or it can also be plus or minus e. Okay. Now this quark exist in groups. So exist in group. So only then you can have the quantization of charge. This is also 0e is also possible. That means zero charge. For example, Q, which is the quark, and another quark and another quark. So this is let it be 2 by 3e, again 2 by 3e, and again let it be minus 1 by 3e. Now together you have equal to minus 1e. So this is how it exists. Okay. Now coming to the 6 flavors. 6 flavors of quark. Now what are these 6 flavors of quark that are up? Now it is given by U, and corresponding to up you have the down, which is given by D. Now another quark is charm, which is given by C. Again strange, which is given by S. Top, which is T, and bottom, which is B. So these are 6 different flavors of quark, and you can categorize them in 3 different generations. So this is the first generation, this is the second generation, and here you have the third generation. And all the what we have written on the upper portion, that is the up charm and the top. These have the charge Q is equal to 2 by 3 times E, and all what is in the down part, that is the down, strange, and bottom, all these have the charge equal to minus 1 by 3 times E. Now there is a note: each charge or each quark exists in 3 colors, that are red, which is R, green, which is G, and blue. Now this is color is just the color quantum number. It has nothing to do with the frequency or the wavelength. It is just the color quantum number, just a like spin. And this color quantum number is called color charge quantum number. So let us write here color charge quantum number. It's a single word, not different. It is color charge quantum number. Color charge quantum number. Now, according to the spin quantum number, we say that no two electrons can have same spin in a state. In a single state or single energy, you cannot have two electrons with the same spin. Similarly, no two quark can have same color charge quantum number. Color charge quantum numbers. Okay. Now, to justify this, we have let us take the case of proton. Proton, which is determined by P, has a charge equal to +1 times E, and this is a spin half particle. Now the proton can be written as up, up, and down. Now let us see what is quark says. It is 2 by 3 times E, and again up is 2 by 3 times E, and down is -1 by 3 times E. So the net charge on this proton is sum of these charges, so that is will be equal to +1 times E. Okay. Now each of this U and D, this will be either green. If this is green, this should be red, and this should be blue. Okay, so all three quarks are different, having different quantum numbers, that is color charge quantum number. Coming to the case of neutron, which is given by N, has charge. Neutron is a neutral charge particle, so charge equal to 0, and it's a spin half particle again, spin half. So neutron is made up of d, d and u, that is dd and up. We will be dealing with the only first generation quarks quarks, so it will be mostly u, d, and we will also deal with the s, second generation strange particles. Okay, these are the only system that we are going to deal with: the up quark, down quark, and the strange quark. Now ddu has got minus 1 by 3 times e. Again this is minus 1 by 3 times e, and up is having 1 by 3 times, sorry, 2 by 3 times e. So sum of the charge is minus 1, and plus 2, which is equal to 0, and it is a spin half particle. Same here, we have either if it is up is red, this, sorry, down is red, then the again the next one should be red, sorry, green, the other one should be blue. Coming to the leptons, these are class of elementary particle, that is one classification of elementary particle which the spin of the leptons are half, and these are again fermions with the spin which is equal to half, and the charge is either q equal to 0 or q equal to minus e. Unlike the quarks, which are not the free particle, leptons are free particles, and they can exist independently, free particle. And what are the particles? Let us see. These are electron and the electron neutrino, and muon and the muon neutrino, and tau and its neutrino, which is mu tau. Again we can classify them. These are exist in 3 generations or 3 groups, and the first part of the leptons, that is electron, muon and tau, has the charge q equal to minus e, and neutrinos, as you know, it is chargeless particle with the q equal to 0. And one thing you have to remember here, leptons do not have color charge quantum number. Do not. Quantum number. Because they exist as single particle, they cannot be further divided into some of the other particles. No, this is the most elementary particles existing. Now potential between the leptons is given by leptons, V is equal to Ke square by R, and potential between quarks V equal to minus A by R plus BR. A and B are some constants. This is in general the electrostatic force or electrostatic potential. Leptons also have its antiparticle. Antiparticles. Now, if we consider the electron and the electron neutrino, the muon and muon neutrino, and tau and tau neutrino, these are one class. These are the, if you consider, these are the particle. Another group of particle exists which are called the antiparticle of leptons, which are E plus, that the positron, and nu E bar or mu plus or mu bar or tau plus or nu tau bar. Now these are the antiparticles. The particle and antiparticle, the only difference is in charge. Here the charge is negative, and for the antiparticle the charge will be plus. And for leptons, you can identify it as a particle by the minus sign, and for antiparticle you can identify it by the plus sign or the bar symbol available on the particle. Okay, so this is bar. So all bars are antiparticle. Coming to the elementary particles, the classification. So classifications. Now here you have the leptons, and on the other side we have hadrons. Now leptons are a free particle, and we have electron, muon and tau, and its neutrinos, electron neutrino, muon neutrino and tau neutrino. Okay. Now its antiparticle, that means the anti-leptons, we have the positron, the mu E bar, its neutrino, mu plus and mu bar, and tau plus, nu tau bar. Okay, so these are the antiparticles associated with the leptons. Now another class of elementary particle is hadrons. Here you have the two kinds of hadrons. Either it is 2 quark or 3 quark. So hadrons can be classified on either it can have 2 quark or 3 quark. Okay, so 2 quark are quark and the anti-quark. So spin is equal to 0, and here for 3 quark it is quark, quark and the quark. No antiparticle exists, so spin is either half or 3 by 2. Now for spin 0, these are called mesons or bosons, and for 3 quark it is called baryons. For 3 quark group they are called baryons, while 2 quark group it is called mesons. Coming to the hadrons, we have hadrons as discussed. It has either 2 quark or 3 quark group. Now if it is a 2 quark, these are called mesons. Now the main mesons are pi, k and eta. These are the main mesons. Spin of meson is equal to 0. Now what are the meson groups? We have pi plus, pi naught and pi minus. This is the one group. And k group, which is k plus and k naught, and k minus and k naught bar. This is the 2 groups. And eta naught is the another meson group, and this is having single particle group. And coming to quark, 3 quark group, we have either it is spin half or spin 3/2 group. So for 3 quark we name it as baryons. Now this can be spin half baryon or spin 3/2 baryon. Now spin half baryons are proton and neutron. So this is the group 1. Then sigma plus, sigma naught and sigma minus. This corresponds to the group 2. And eta naught and eta minus, this is the group 3. And lambda naught, it is the group 4. That is the single particle group. Okay, so lambda naught, this is lambda. Okay, now all these are spin half, and this forms octet. Okay, this is the structure formed by spin half baryon. And similarly, since there are 8 particles here in meson, they also form octet. Now this we will discuss in some time. Now spin 3/2. Now what are spin 3/2 particles? Now spin 3/2 particles are delta double plus, delta plus, delta naught and delta minus. This corresponds to the group 1. Okay, now second one is sigma plus star, sigma naught star and sigma minus star. So this corresponds to the group 2. Now cascade naught star and cascade minus star and omega minus. So this is the group 4. So since there are 10 particles, they form decuplet. Coming to the conservation laws. Now first conservation is conservation of lepton number. Now for all leptons, and the lepton number is +1 for all leptons and -1 for all antileptons. Now what are these leptons? Leptons are electron, muon, tau, and its neutrino, electron neutrino, muon neutrino, and tau neutrino. And what are these antileptons? Antileptons are its antiparticle, positron, muon plus, tau plus, mu e bar, nu mu bar, and nu tau bar, and 0 for all others. Now, for lepton number, you have to classify the lepton number as L, E, L mu, and L tau. That means the lepton number for electron particle, lepton number for muon particle, and lepton number for tau particle. So for electrons, for Le, so the electron and nu e, its neutrino, are +1. Okay, so for this is for +1 and -1 for its positron and nu e bar. For both positron and nu e bar, Le is -1. L mu, that is the lepton number for mu. Here also you have +1. Here you have -1. Now, this is for mu minus and nu mu. This is for mu plus and nu mu bar. And here you have +1 for tau minus and mu tau, and -1 for tau plus and nu tau bar. So on the left side you have the particle and on the right side you have antiparticle. Okay, in all these lepton numbers. So this is conservation of lepton number, and on the for any reaction, the lepton number on the LHS, that means the left hand side, should be equal to, that means the lepton number on LHS should be equal to lepton number for RHS. This lepton number, if you have electron particle, it should be Le. If you have muon particle, it should be Mu. Mu on LHS should be equal to L mu on RHS. Okay. Similarly for tau. Another kind of the conservation law is conservation of baryon number. So conservation of baryon number. Baryon number is represented by B, and this is +1 for all baryons, -1 for all antibaryons. Antibaryons are represented by bar. Example is like this bar. Good example is lambda naught bar, proton bar, and omega minus bar, etc. Okay, so if you have bar on the baryons, it will be an anti-baryon, and 0 for all other particles. All other particles are leptons or mesons. So the baryon number is 1 for all baryons. So all baryons are either it is a spin half baryon or it will be spin 3 by 2 baryon. So for spin half baryon you have neutron and proton, then lambda naught, sigma plus, sigma naught and sigma minus, and cascade naught and cascade minus. So these are 8 spin half baryons. Coming to spin 3 by 2 baryon, we have delta double plus, delta plus, delta naught and delta minus. This double plus, plus, naught and minus indicate the charge. Double plus means plus 2 electron, plus 2e, and naught means it is 0 charge. Delta minus means minus 1 e charge. Okay, then you have sigma plus star, sigma naught star, and sigma minus star, and you have cascade naught star, cascade minus star, and omega minus. So these are 10 particles and these are 8 particles, and these are the particles, that means spin half and spin 3 by 2 particles which have baryon number equal to plus 1. All other anti-baryons, for example delta double plus bar, then sigma naught bar, all these particles have the baryon number equal to minus 1. Apart from whatever we have in these groups, these two groups, all other particles represented by the baryons, then baryons with a bar, you will have minus 1 as the baryon number, and for others, leptons and mesons, the baryon number is 0. The another kind of conservation law is isospin conservation. The isospin is given by the letter I. So it depends, the isospin is given to the type of the interaction. For leptons, since they are weakly interacting particles, for leptons the isospin is equal to 0. So I is equal to 0 for leptons, and for hadrons the isospin is given by, for hadrons you have isospin, and it is determined by number of particles in a group. Particles in a group. Now, for example, if you have pi naught, so this is only one particle, so the isospin I is equal to 0. And for two particle system, for example neutron and proton is belong to the same group, so the isospin equal to half. And for three particle group such as pi plus, pi naught, pi minus, the isospin equal to 1. And for four particle groups such as delta double plus, delta naught and delta minus, the isospin I equal to 3 by 2. So isospin is given by number of particle minus 1 divided by 2, that is I is equal to n minus 1 by 2, where n is the number of particle in a group. N is number of particle in the group. Now one thing you have to remember, that for leptons isospin equal to 0. These are only for hadrons. Only for hadrons the isospin exists. Now for all particle, now you have to, what you have to remember is, for all particles in the group, has same isospin. For example, the neutron and proton has the isospin equal to half. Pi plus, pi naught and pi minus has isospin equal to 1. And delta double plus, delta naught and delta minus, all the four particles in this group has isospin equal to 3 by 2. Fourth one is the third component of isospin. So third component of isospin is given by I3, and the value of the third component, or it is also given as Iz. Okay, now I3 is equal to Q minus Q bar. Now the Q is the charge of the particle, and Q bar is the average charge of the group. Okay. Now just for example, we will consider the group pi plus, pi naught and pi minus. Now in this we know the I is equal to, that is the isospin equal to n minus 1 by 2, so that's equal to 1. That means pi plus, pi naught and pi minus has the isospin equal to 1. Then I3 of let us take I3 of pi naught. Okay, now for that you need the charge of the pi naught, Q of pi naught, minus Q bar. Now what is Q bar? Q bar is the average charge, so that's equal to the charge of pi naught equal to 0 minus average charge here. In this, average charge means the sum of the charges, so sum of the charge by number of particles, sum of charges divided by number of particles. Now the sum of charges is plus 1 plus 0 minus 1 divided by the number of particle is 3 particle. So plus 1 plus 0, that is 1, minus 1, that is 0. So average charge is 0. So 0 minus 0. So I3 for pi naught equal to 0. Similarly for I3 for pi plus will be equal to plus 1 minus 0, that is equal to 1, and I3 for pi minus will be equal to minus 1. In this slide we will see different mesons and corresponding I and I3. So mesons we will start with pi plus, pi naught, pi minus, and all have the value of the isospin equal to 1, 1 and 1, and I3 is nothing but q minus q bar. So you know that for 3 particles, that is plus 0 and minus 1, q bar average value is 0. So I3 is plus 1, 0 and minus 1. So I3 is plus 1, 0 and minus 1. And for k plus and k naught, both have 2 particles. So this is half and half, that is the isospin is half, and q minus q bar. Q bar here is half. Is it? Yeah. So q minus q bar, and q bar, q is here plus 1 for k plus, so 1 minus half is half, and this is minus half. Now k minus and k naught bar, so this is another group. So this is one group, k plus and k naught is one group, and k minus and k naught bar is another group. And here also the isospin is half and half, and here you have k minus, which is minus half, and this is plus half. And for another meson is eta naught. For eta naught, since it is a single particle system, it has got a 0 isospin, and similarly the I3 third component is also 0 for eta naught. For spin half baryon, we have the particles such as the proton, neutron, the lambda naught, sigma plus, sigma naught and sigma minus, and cascade naught and cascade minus. Now I, which is the isospin of proton and neutron, are half and half. Lambda naught, there is no isospin, so it is 0. Sigma plus, sigma naught and sigma minus, so it is a 3 particle group, so it will have 1, 1 and 1 as the isospin. Since cascade naught and cascade minus are 2 particle group, it will have half and half. Now the third component of isospin for proton and neutron, it is so it will have the plus half, the first half, and the next minus half. I3 is 0 for lambda naught, and here for sigma plus, sigma naught and sigma minus, it will be minus 1, 0 and 1. And for cascade naught and cascade minus, it is minus half, sorry, it is plus half and minus half. For spin 3 by 2 baryons, the particles are delta double plus, delta plus, delta naught and delta minus, which forms the group, the 4 group. And sigma plus star, sigma naught star, and sigma minus star makes the second group, and cascade naught star and cascade minus star makes the third group, and omega minus the last group. So I for 4 particle group is 3 by 2. So all the particle of this 4 particle group has got 3 by 2 as the isospin. For 3 particle group it is 1, 1 and 1. For 2 particle group it is half and half. And for 1 particle group isospin is 0. Now the third component of isospin for the 4 particle group that is delta double plus, it is plus 3 by 2. Now comes plus 1 by 2 and minus 1 by 2 and minus 3 by 2. So it goes in this order. And for 3 particle group, starting with sigma plus star, we have plus 1, 0 and minus 1. And for 2 particle group, starting with sigma naught star, we have half and minus half, and the isospin third 0. Another kind of quantum number is the strangeness quantum number. This quantum number is associated with strange particles. Strange particles, and why they are called strange particle? Because they have faster production. These particles get produced very faster, so it is faster production of the any particle and slower decay, and they decay very slowly. So this is why they are called strange particles. Examples of strange particles are K plus and K naught. This is one group. Lambda naught is also an example of strange particle. K minus and K naught bar, these are the antiparticles of the first group. And sigma plus, sigma naught and sigma minus, these are also strange particle. We will discuss about the strangeness of this particle very soon. Cascade naught and cascade minus, these are again strange particles. Similarly, sigma plus star, sigma naught star and sigma minus star, all these are also strange particles. And corresponding to cascade, cascade naught star and cascade minus star are also strange particles. Along with that, omega minus is also strange particles. Now, some of the characteristics of the strange particles are, these are formed by strong interaction. And decay through weak interaction. Now, as always, the particle and the antiparticle have opposite strangeness quantum number. Opposite. Now one good example is K plus. K plus have the strangeness quantum number equal to 1 and its antiparticle is K minus. So K minus will have the strangeness quantum number equal to -1. This is one example of the last point we discussed. The particle and antiparticle have opposite strangeness quantum number. Now here let us see the strangeness and the type of the particle in the group we have discussed now. Now for K mesons we have the strangeness equal to 1, positive 1 plus 1, and the particles that belongs to the K mesons group are K plus and K naught. K anti-mesons, the antiparticle, so its strangeness as -1, and it is the particles are K minus and K naught bar. Lambda, the particle is lambda naught and the strangeness is -1. Okay. And the sigma group, again they have the strangeness equal to -1 and sigma plus, sigma minus, sigma naught, let us write naught here and minus here, and sigma plus star, sigma naught star and sigma minus star. These are the particles that corresponds to sigma group. Now cascade group, the strangeness is -2 and the particles are cascade naught, cascade minus, cascade naught star and cascade minus star. For omega minus, the strangeness is -3 and the only particle that is available in omega group is omega minus. So these are the different groups, their strangeness and the particles for different groups. Gelliman-Nishijia formula. Gelliman-Nishijia. Now this formula is to find the strangeness of the particle. Now this is given by Q, this which is the charge, is equal to I3 plus B plus S by 2. Now here Q is the charge, I3 third component of isospin, B is the baryon number, S the strangeness quantum number. So here we are discussing the quark structure of mesons. So mesons quark structure. So this is very important. You will get everything in one single structure. So quark structure, and this is called octet because there are 8 points here, and one more point is at the center. So all this 1 2 3 4 5 6 7 and 8. Now all particles have to be embedded in this structure. Now we'll start with the K plus and K naught. So K plus, K naught, these are two particles, and K minus, or sorry, it's K naught bar on the right hand side, and towards here it is K minus, and here you have pi plus, pi naught and pi minus. So when you move from right to the left, there is a decrease in the charge, or this has to be written in the form of decreasing charge from right to the left. Okay, and you also have one more meson. What is that? That is eta naught. So what are the mesons? K plus and K naught, and here you have K naught bar and K minus, pi plus, pi naught and pi minus, and also you have eta naught. So in total you have 8 meson particle, and that is what we have written here. Now we need the quark structure. The quark structure, we deal with up, down and strange particle, or strange quarks, up, down and strange quarks. We are going to write down this up, down, and all these mesons structure. That means the constituents of mesons. What is mesons made up of? So starting with K plus, you have U S bar, U S bar. Now it is up quark and the anti-strange particle, U S bar. Okay, now here you have U D bar, up and anti down quark. All right, now here K naught D S bar, here D U bar, and here S U bar and S D bar. So from this you can understand that wherever there is S, it indicates it is a strange particle. So we know that K plus, K naught bar and K minus are strange particle, while whatever is on the other side, it is not a strange particle. And what is this eta naught and pi naught made up of? Eta naught and pi naught are made up of two quarks, which are the quark and the anti-quark, U bar, or it can be D bar, or S bar. It is not a strange particle. Eta naught and pi naught are not strange particles. So this is how you can remember the quark structure, starting with U you have u here, u, d, d, s and s. And after once you done with the first quark, your next quark is d bar, which is just the antiparticle of d over here. So d bar, s bar, s bar, u bar. So just find out the other opposite particle or opposite quark and write down. So one example, here you have u d bar, and the opposite side is this one, and here you have du bar. Similarly, you have here ds bar, and opposite is here, which is s d bar. Okay. So if you can picturize this in your mind, you can get any particle, charge, strangeness, everything. So here look at this. If you draw a line over here like this, there are two mesons here, that is K plus and pi plus. These are the only two positive mesons present in the entire structure, K plus and pi plus. Now look at this line here. You can draw one line over here which passes through the center and move to this side. Now if you draw this line, you can find K naught, pi naught, eta naught and K naught bar. These are the charged particle with charge 0. Now draw another line over here, pi minus and K minus, and these are the two particles with negative charge. Coming to the quark structure of the spin half baryon. Quark structure for spin half baryon. Now this is also an octet because there are 8 spin half baryons. What are spin half baryons? You have proton and neutron, then you have sigma plus, sigma naught, sigma minus, which is another set of spin half baryon. Then you have cascade naught and cascade minus, and also you have lambda naught. Now as we have done with the meson quark structure, we have 8 particles that has to be embedded here, and starting with the proton, which is charge plus 1 charge, so proton here, and correspondingly neutron will come here. So only other, this is proton has plus charge, neutron is 0. So proton plus, just to indicate it is a positive charge, we will write like this. Now another positive charge from this set is sigma plus. So once you have sigma plus here, you need to write sigma naught and sigma minus here. So we have completed 2 groups, and another particle which has 0 charge we will write here, which is lambda naught. Right now here you need to write another charge which has 0 charge over here, so it is cascade naught with 0 charge, and here you need to have a particle with -1 charge, which is nothing but sigma minus. So we have incorporated all the particles, spin half baryons in the octet. Now our aim is to find the constituents, that is the quark structure, or what is each spin half baryon made of. So I will start with sigma plus, which is U, U and S. U, S. And here again I will write all the first two quarks available, UU, and here neutron is DD. One more quark is there, we will write down that, and here again DD, and here you have SS, here you have again SS. So one more quark is there to be written in all the baryons, but time being we stop it there. So UUS. Now once UUS we have written, now you start with UU. Look at the next one, UUS we have written, it is now D. Now DD, after DD it is U. Now once DD is complete, DDS, SS, again SS it is D, and SS U. Okay, so what is left after UU? We have written S, UU, D. Now DD, U, DD, S. Okay. Okay, fine. So that's it. So from here you can understand that, and in the center you have UDS. It is a combination of all the particle UD and S, quarks. Now you can understand which all has strangeness equal to 1. With only one S quark, single strange quark, you have strangeness equal to -1. Okay, so sigma plus, that is here, sigma naught, sigma minus, as well as lambda naught, all have single strange quark. So which is means all these particles have strangeness equal to -1. Coming to the lower part, that is the cascade naught and cascade minus, they both have two strange quarks. So they have SS and SS. So two strange quarks, so their strangeness equal to -2. So this is how you can find the strangeness, the charge of the quarks and the group in which they belongs to, by using the structure, quark structure. Here we are discussing the quark structure of the spin 3/2 baryon. So we have the spin 3/2 baryon and quark structure. So coming to what are the spin 3/2 baryons, we have delta double plus, delta plus, delta naught and delta minus. Sigma plus star, sigma naught star, sigma minus star, cascade not star, cascade minus star, and omega minus. Now starting with the left side corner, we have delta double plus over here, and that's the only baryon with 2 positive, I mean 2 plus charge, so delta double plus, so that's in the one end. Now here you have delta plus and delta not, delta minus. So these all lines, this is 1 2 3 4, this all will have minus charge. This one delta plus here, and this one also will have positive charge. Here you have neutral charge, all the 3 lines. So if you want, we can just let it pass by this way, 2 lines. Okay, now with that we have done with delta double plus. Now we have the next positive charge, and there is only one more positive charge, which is only sigma plus star, which is positive. And once you know that this is sigma plus, here also it will be this will be sigma naught, and this will be sigma minus, because it should have negative and this should be neutral. And now this one should be zero charge, and you know that delta naught and sigma naught star. Okay, here we need to write star, because if you don't write star, this belongs to spin half baryon. Okay, now it is spin 3/2 baryon. Now once you have completed that, you have cascade not star, again this is neutral charge, and after that you have cascade minus star, and once you are completed with all other, we have only one left, that is omega minus. Now coming to the quark structure of which it is made, it starts from U and U, and slowly it becomes UUD and UDD, increase in D and decrease in U, and it is completely D, D and D. So it starts from UUU and ends in DDD. And for the next one, sigma plus star, it is now let us start from DDD and reach omega minus. So starts from omega and it should reach yes. So this is yes, 3 yes, and you can understand this strangeness of this omega minus is -3. So starts from DDD and you have to end here, so it will be DDS, DSS, and finally you reach yes. Now from yes to UUU. Now yes U, yes UU, and finally you reach UUU. And the middle one you have sigma naught star, which is the combination of UD and S. So this is how you can get the strangeness, charge of all the baryon and meson from the quark structure. How to identify the type of reaction? Now there are different kinds of reaction, like we have strong interaction, then we have electromagnetic interaction, then weak interaction. Now all these interactions are based on the type of the particle produced. Type of particle produced or involved in a reaction. So based on the type of the particle or the conservation laws, so actually this belongs to the conservation laws. According to the conservation laws, we classify them as either strong electromagnetic or weak interaction. Now, as discussed, we can find out the type of interaction based on the conservation laws. Now, here we have the type of interaction. And here we have the quantum numbers, the charge, which is given by Q, and lepton number, which is given by L, and the baryon number, which is given by B. So QLB, and these are called primary quantum numbers. Now for any interaction, primary quantum number is conserved. So primary quantum numbers. So, and apart from that, we have the isospin I, third component of the isospin, which is I3, and the strangeness quantum number, which is S. Now here we have the strong interaction, that is the type of interaction, electromagnetic interaction, and weak interaction. Okay, now as said, for whether it is strong electromagnetic or weak interaction, all the primary quantum numbers should be conserved. So all are conserved for strong electromagnetic and weak interaction, that are the primary quantum numbers. And in the case of isospin, for strong interaction, isospin, either it can be conserved or not. Both are possible. Either you can have the isospin conserved or not, but the third component of isospin has to be conserved, and the strangeness also has to be conserved. Okay, now for electromagnetic interaction, it is need not be conserved. Okay, so that's why we have 0 here, which means need not be conserved. Then both I3 and the strangeness quantum number has to be conserved. And for weak interaction, there is no need to conserve the isospin and its third component, and the delta S, that is the strangeness quantum number, either it can be equal to plus or minus 1 for weak interaction, either it has to be equal to plus or minus 1 or conserved, delta S equal to 0, which means it is conserved. Okay, so to remember, for strong interaction, all the quantum numbers are to be conserved. So if all the quantum numbers are conserved, you can say it's a strong interaction. For electromagnetic interaction, the isospin need not be conserved. Even if it is not conserved, you can say that it is an electromagnetic interaction. Okay. Now for the weak interaction, the isospin and third component of isospin need not be conserved, and the delta S value should be plus or minus 1 and or equal to 0, which means it is conserved. Here we can have some notes regarding the type of interactions and the characteristics of the interaction. Now first one is, if any one of primary quantum number, and that is either charge or lepton number or baryon number, is not conserved, then the reaction is forbidden. Second one is, for a strong interaction, the particles must be hadrons. All particles must be hadrons. All particles taking part in the reaction must be hadrons. And it should not contain leptons. Now the second point in this regard is, that is based on the strong interaction, is associated productions. That means the particles formed in this reaction, it should be two or more strange particle. Two or more strange particle must be produced. That means on the RHS you should have two or more particles. Okay, so right hand side you should have two or more strange particles. Coming to the electromagnetic interaction, if a photon is present, it is EMI, electromagnetic interaction. So it is, photon is given by gamma, and then it is EMI, and another method to check whether it is EMI is particle and antiparticle present. So if the reaction consists of particle and antiparticle, then it can be or it has to be electromagnetic interaction. And here you can remember that pi naught is antiparticle of itself, which means pi naught, if both are pi naught and pi naught is present, these are termed as particle and antiparticle. Now coming to weak interaction. Weak interaction will have leptons in the interaction. Leptons will be there, and any decay of strange particle, any decay of strange particle is weak interaction. That means, for example, omega minus is decaying to some particles, then this should be a weak interaction. Leptons are present in reaction. If leptons are present in a reaction, this can be that is a weak interaction, and decay of strange particle will be a weak interaction. So these are how you can classify or find out the type of interactions from the particle involved. Apart from the conservation laws that we have, we also have the conservation of linear momentum conservation in any particle reaction. For example, we consider the positron and electron interaction giving gamma. Now this reaction is not possible unless there is one more gamma, which contributes to the conservation of linear momentum. And similarly, we have the angular momentum conservation. For angular momentum conservation, we are dealing with spin of the particle, spin angular momentum, which indicates that the number of fermions on left hand side should be equal to number of fermions on right hand side. Or in general, we need to understand that NH cross on left hand side should be equal to NH cross on right hand side, okay, or NH cross by 2 for this is on right hand side, this should be on left hand side. Now we also have charge parity and time reversal quantum number. This also has to be conserved. C is charge, P is parity, and T is time. Now charge conjugation, we talk about the conjugation of charge, where Q changes to minus Q. Parity inverse where R, the position, changes to minus R, and time reversal where T changes to minus T. Okay. So individually, when charge changes to minus Q or Q changes to minus Q on charge conjugation, your equation should satisfy, or the reaction should be conserved. That means Q should be conserved. Delta Q should be equal to 0 for charge conjugation, and delta R, that means also should be equal to 0. That means there is no change in the reaction when parity changes or when time changes. it's not about delta t or delta r equal to 0, equation remains same or reactions remains same. This is what is meant by charge conjugation. Here also the equation remains the same. Alright, now considering the type of interaction, we have the strong interaction, electromagnetic interaction, and weak interaction. And here we have charge, parity, and time reversal. And here we have all together charge, parity, and time reversal in one go. Now for strong interaction, when charge conjugation, the interaction remains same. It is true for EMI, electromagnetic interaction, and it is not true for weak interaction. It need not be considered. For strong interaction, parity, time reversal, as well as CPT, this is together, it should be conserved. Now for electromagnetic interaction also, parity, time reversal, and together it is also conserved. And for weak interaction, individually it need not be conserved, but the together, CPT together, must be conserved. Parity is given by parity is equal to -1 whole to the power L, where L is the angular moment.